Hi there, Dr. Givens here, and I'm going to be recording some videos to help you get ready for the AP Calculus exams. This first one is going to be for BC, and I've got up on the screen a website that shows a list of the topics that are remaining still in play for your 2 free response questions. At the top there, and then at the bottom you'll see where it says Unit 9 and 10, the material that is no longer going to be tested. So from Unit 9, parametric equations, polar coordinates, and vector-valued functions. And then certain subtopics from Unit 10, infinite sequences and series. But, to be clear, up in the middle of the screen, you'll see the remaining topics from Unit 10, geometric series, harmonic series, p-series, alternating series test, the ratio test, and finding Taylor polynomials. And so today what I thought I would do is share with you my solution to a former free response question that involves several of those topics, actually, as well as some from Unit 7 on differential equations. This is from 2010, Form B, and it's question number 6, which is usually the question that has a power series or infinite series involved with it. So here's the question. Pause the video if you want. Take a minute to look through and see what it says. If you want to try it out on your own, now's the time. But once you've done that, let's now go and I will share my own solution with you. All right. Sorry about the glare. My students are used to that. I'll avoid writing over that area. The power series gives a function. It's defined by the sum from n equals 2 to infinity of -1 to the n, 2x to the n, divided by n minus 1. And we're asked in part A to find the interval of convergence. In order to do that, we're going to use the ratio test. That's the typical way to do this if the series you're working with isn't already a geometric series, which this one is not. So to find the interval of convergence, I will find this quantity that I like to call rho, which is defined as the limit as n goes to infinity of the absolute value. Sometimes the book will call this the absolute ratio test, but I just think of it as the ratio test. The absolute value of a sub n plus 1 divided by a sub n. And since this is a power series, the a sub n plus 1 in this formula is what I'm thinking of as this entire thing, including the x to the n. So the whole thing is a sub n. And if I replace n with n plus 1 in the whole thing, that's a sub n plus 1. So that looks like the limit as n goes to infinity of the absolute value. And it's going to be a big fraction with a fraction on top and a fraction on bottom. So on the bottom fraction, it's exactly this thing again, a sub n. So -1 to the n, 2x quantity to the n divided by n minus 1. On the top here, I replace all the n's with n plus 1. So it'll be -1 to the n plus 1, 2x to the n plus 1, divided by n plus 1 minus 1, which is just n. And then I simplify this by rewriting the division of two fractions as a multiplication with the bottom fraction flipped, like we learned in grade school. It's going to be the limit as n goes to infinity of the absolute value of... before I keep going, let me just note that since I'm taking an absolute value, these -1 to the n's, which are otherwise going to be either plus or minus 1, those will get killed by the absolute value to just be positive 1, so I can ignore them going forward, right? Whenever the absolute value got applied to these, they would become positive 1. So the top here is going to be 2x to the n plus 1, and then times n minus 1. The denominator will be 2x to the n times n, absolute value. All right, and this is the place where you now want to see if there's any cancellation, and there is. I've got a 2x to the n plus 1 on top, a 2x to the n on bottom. When that cancels, it's just going to leave me 2x on top. So limit as, don't forget to keep writing the limit symbol. Limit as n goes to infinity of 2x times n plus 1 divided by n. And now I can see that this 2x here is not got any n's in it. I'm taking a limit with respect to n, so the n's have got to stay inside the limit, but this 2x is a constant that can be pulled outside of the limit. I got to keep the absolute value on it, so it's the absolute value of 2x times the limit as n goes to infinity of the absolute value of, this was supposed to be n minus 1, of n minus 1 over n. Not going to make a difference to the end result, because the limit as n goes to infinity of n minus 1 over n is a pretty easy limit. That's just 1. So limit is 1, so this whole expression works out to be 2, absolute value of 2x, or this, what's the same thing, 2 times the absolute value of x. That's my value rho. And now if you remember what the ratio test says, it says that when rho is less than 1, which means that this next term that you're adding up is somehow in the limit is much less than the previous term. So these are going to 0 at a rapid clip. If this rho is less than 1, your series converges. If it's greater than 1, your series diverges. And if it's equal to 1, your series, the test is inconclusive. You don't know. So what we've learned is that my series converges absolutely. Converges absolutely when this quantity right here, 2 absolute x, is less than 1. Which is just another way of saying that absolute x is less than 1/2, or negative 1/2 is less than x is less than positive 1/2. So if I had just been asked about the radius of convergence, then I'd be done. The radius of convergence is the distance from the center of this power series and interval, 0, out to one of the edges, so the radius of convergence is 1/2. But I'm asked for the interval of convergence, which means I need to know, does it converge at these two endpoints, plus or minus 1/2? I've got to test them separately because those are exactly the locations where the ratio test gives me rho equals 1, and so it's inconclusive at the endpoints. So let me erase the screen magically. And I'm going to test the endpoints separately. So test the endpoints separately. Test the endpoints. So the first one is x equals 1/2. That's the first endpoint. And I just plug it into this sigma expression. So sum from n equals 2 to infinity of negative 1 to the n times 2 times 1/2 to the n divided by n minus 1. 2 times 1/2 is 1. Raised to the n is still 1. So this simplifies to n equals 2 to infinity, negative 1 to the n divided by n minus 1. And if it wasn't obvious what's going on here, you might try plugging in the first few values. Negative 1 squared is positive 1, divided by 2 minus 1 is 1. The next term will be minus 1/2, plus 1/3, minus 1/4, etc. Dot, dot, dot. That's, now it's quite clear that this is the alternating harmonic series, 1 minus 1/2 plus 1/3 minus 1/4. And you can remember that converges. The alternating series converges conditionally. And you can just, the justification is, it's a well-known series. You can just note that it is the alternating harmonic series and therefore converges. Now let's try the other endpoint, x equals negative 1/2. It's going to be the sum from n equals 2 to infinity of negative 1 to the n, 2 times negative 1/2, all raised to the n, divided by n minus 1. So now we've got negative 1 to the n and then it's going to be times negative 1 to the n over n minus 1. Here I'm going to cheat a little bit. Negative 1 to the n times negative 1 to the n for any particular value of n is going to be either 1 times 1 or negative 1 times 1. Negative 1 times negative 1, which is 1, regardless. So if I write out the first few terms of this, it is 1 plus 1/2 plus 1/3 plus 1/4. This one is just the ordinary harmonic series, which diverges. Okay, I've tested both the endpoints, found out what the series does at each endpoint, and I'm ready to write my final solution here for the interval of convergence. My series diverges at negative 1/2, so I keep the less than sign, but it converges at the other endpoint, positive 1/2, so I'll make that a less than or equal to. That is my interval of convergence. All right, let's try part B now. So I've kept my power series right here, and on this side I've written the differential equation. Part B asks us to show that the power series function y, defined this way, satisfies this differential equation, is a solution of this first order differential equation. If you're in my differential equations class, you might be thinking it's a linear first order differential equation. I don't recommend using integrating factor to solve this. And in fact, that's not part of the AP Calculus curriculum. Instead, we will solve it by manipulating this power series, which you should also be pretty comfortable with if you're in my differential equations class. So this is y, and therefore y prime, when I differentiate with respect to x, I'm going to get the sum from n equals 2 to infinity, negative 1 to the n. It's term-by-term differentiation, so you just differentiate each summand, each expression like this. 2x to the n is the same as 2 to the n times x to the n. And so I've got x to the n, I'm going to differentiate that function in each summand. So x to the n is, derivative is nx to the n minus 1 divided by n minus 1. All right, so that's y prime. And now what I'm going to do is plug these power series expressions for y and y prime into this side here, and hope that I can manipulate it in such a way to get the right-hand side over here. Let's try. So, and I'm going to cheat a little bit, right? This is y prime, so I'm going to use it as this y prime, and I'm going to write x y prime minus y. So it's x times this expression minus the expression for y. N equals 2 to infinity, negative 1 to the n, I'll write 2 to the n, x to the n this time, divided by n minus 1. Okay, that's the left-hand side of my differential equation, and I'm going to try and simplify it to make it the right-hand side. First thing I need to do is bring this x inside and make it part of the summand, and I will, and then I'd like to combine these two summands, these two sigmas, into a single sigma. So I'll bring this x inside. It looks like now the sum from n equals 2 to infinity of negative 1 to the n, n x to the n over n minus 1, minus the sum from n equals 2 to infinity, negative 1 to the n, 2 to the n, x to the n, divided by n minus 1. And the beautiful thing now is that these x to the n's are matching. And also, I'm lucky, the sigmas are starting at the same place as each other, both at n equals 2. So I can just merge these together and get the sum of, not the sum of this minus the sum of that, but the sum of this minus that. And if I do, I'm subtracting two fractions, right? and the denominators match, so I'm just going to subtract across the top. -1 to the n. I lost a 2 to the n here, guys. Let me fix that. 2 to the n and x to the n should have been right there from there. -1 to the n, 2 to the n, x to the n, minus -1 to the n, 2 to the n, x to the n. And then you might notice that almost everything on the top is the same. Hopefully I have enough room here. I'm going to factor out the stuff that's the same on the top. Namely, -1 to the n, 2 to the n, x to the n. And there's an extra factor of n, and no extra factors there, so it's going to be n minus 1 gets factored out. So -1 to the n, 2 to the n, x to the n, times the quantity n minus 1. And once you get here, you know you're doing something right because these are canceled. These will cancel right out, and I'm left with the sum from n equals 2 to infinity of -1 to the n, 2 to the n, x to the n. Let me write that by itself up top. All right, and since everything is raised to the n, I can simplify that to be just -2x quantity, all raised to the nth power. And this is looking really nice. You'll notice I have an infinite sum of some specific thing without any n's involved raised to the n. You might remember that that is a geometric series. Or if you write it out, maybe it'll be more obvious. -2x squared plus -2x cubed plus -2x to the 4th plus etc. forever. First term, -2x quantity squared. The common ratio is -2x. To get from one term to the next, I'm just multiplying by -2x every time. Formula for the sum of a geometric series is first term over 1 minus the common ratio. Remember, a over 1 minus r. My first term again, -2x quantity squared, divided by 1 minus common ratio of -2x, and that simplifies to 4x squared over 1 plus 2x. Yes.